Say you have some data you want to classify. This data could be of any type. The raw pixel values of an image, the raw samples of attractive audio, a portion of text, as long as it can be represented as an array of a fixed amount of numbers. You want to use a neural network to classify your data, so you construct the first one that comes to mind, a perceptron. This single-layer perceptron takes in an array, the vector of numbers that represents your input data, and combines data to produce a single output. Here's an example of how a trained perceptron would classify a given input array. A simple summation of the value of each input neuron would not be sufficient to capture the features of the data, so a weight on the connection between every input neuron and the output neuron must be applied. This weight is a coefficient multiplied with the input value of that neuron. Because the output must range between 0 and 1, this weighted sum must be run through a step function that maps the value to either 0 or 1. With that done, and assuming you set the weights properly, you've now trained yourself a single-layer perceptron. Unfortunately, this single output neuron is only capable of linear classification. That is, it can only map an input to one of two classes, and with only a single linear boundary. Any more complex problems, such as this XOR classification problem, require a more complex neural network. One easy solution would be to add more neurons in a hidden layer. In this case, we'll be using a single hidden layer with 4 neurons. Just as the output neuron encodes a single feature, whether or not the input corresponds to one or another class, each neuron of the hidden layer encodes a single feature. This network has 4 neurons in the hidden layer, and so encodes 4 features. As the step function cannot learn difficult classification tasks, it should be switched for a continuous activation function, like the sigmoid function, which performs the same task, mapping a real input to an output between 0 and 1, but with a gradual shift between 0 and 1 as the input changes. Additionally, a bias may be applied to the output of each neuron before the activation function is applied. Each neuron must be connected to every neuron of the previous layer. Each connection has its own unique weight. Therefore, every single neuron is treated exactly the same. In this manner, you can represent the value of each neuron of a given layer as the weight matrix of the neuron multiplied by the input vector, with the bias and then the activation function of the layer factored in afterward. As such, each layer can be represented in a concise mathematical manner. And with this, we've boiled the entire forward operation of the neural network down into a single matrix multiplication.